Okay, so let's review what we did in the last class. It's a labor-intensive chapter in the sense that there's limited amount of intuition that you can get out of all these numbers, imaginary numbers, complex numbers, um, cosine. They do provide intuition to us, but you have to wrestle with them a whole lot more just to get just to squeeze one drop of intuition out of this. But that's fine. But the sinusoid signals themselves are very they're really nice waves. We find them everywhere, naturally occurring in nature. So it's important that we begin understanding the sinusoids and the different ways of expressing sinusoids, and also different ways in which our electrical systems, okay, respond to sinusoids. This is all important. So let's quickly review. Okay. So I added a page right where we stopped in the last class. Okay. What we started doing in the last class was to look at sinusoid signals, right? As kind of a representative or a running example for us to gain necessary intuition to understand how electrical systems respond to time varying inputs. Okay, and we chose to use the cosine. Okay, this is the time domain representation. Okay, as it turns out, the same wave, the same signal can be shown in two other forms. It can be shown as a phasor, and it can be shown as a complex number. Okay, there's different names to this. You call them in a rectangular form. Okay, in rectangular form. Okay, in order to convert this guy, to phasor, all you have to do is do a phasor transform of this. So when you hear the words like doing a phasor transform, what you're really doing is expressing the magnitude. So the phasor transform of this guy would be the phasor transform of all of this, would be the magnitude and phase angle. Okay, so this is called the polar form. Okay, polar form. And as it turns out, a complex number, okay, so this is the equivalent of this, Vm angle phi in a polar form is the same as Vm cos phi plus J Vm sin phi. Okay, the conversion between polar form to rectangular form. So all of this is based on the Euler's identity. E to the j theta is cos theta plus or minus j sine theta. Okay, so this marriage between trigonometry and exponential function, e and cos theta and square root of -1, it's a magical identity. Okay, it's an interesting identity that we make use of often and often again. Okay, so if you think about this number, this is the rectangular form. FOR form. This is the polar form. Now the real part of this guy, the real part of e to the j theta or j phi, okay, this guy, that's the real part of e to the j phi, right? So this is all e to the j phi, right? Because cos phi plus, okay, so I'm really doing the real part of Vm times e to the j phi, okay? That is cos phi, okay? The imaginary part of this guy is sin phi, okay? And we'll see how to go from one to other. So we couldn't of Vm sin phi, okay? So this is the real part, the one on the top, and the bottom is the imaginary part. Okay? We can do a simple example. Let's say I have 3 plus j4. Okay, when I have 3 plus j4 in the rectangular form, and I want to go to the polar form, I have to find out a e to the j theta, okay? X plus jy, okay, in the rectangular form needs to be converted to a to the a times e to the j theta, okay? So how does that conversion work? And we do enough number of problems on this just so you get very comfortable with the idea. So if you want to convert x plus jy to polar form, then you have to find out a by using the magnitude. The square root of the sum of squares of the real part and the imaginary part. Okay, that gives you a over here. Okay, then how do you find out theta? Theta is tan inverse, okay, arctan of the imaginary part over the real part. Okay, that gives you the theta. Now you have everything that you need to express this guy in polar form. Okay, 3 plus j4 is a times e to the j theta, where a is square root of 3 squared plus 4 squared, which comes out to be 5. Theta is tan inverse imaginary part, which is 4, over the real part, 3. Okay? So you'll find out that you can express 3 plus j4 in the rectangular form as 5 angle 53.1. Okay, 53.1 degrees. That's the conversion. You can go the other way as well. You can go from polar form to rectangular form as well. And that, how to do that, I already mentioned, right? If you have this, to get the real part of this, all you have to do is a times cos of this angle, cos theta, gives you the real part. A times sine theta gives you the imaginary part. Okay, as we will see in the coming examples, when we are going from the rectangular form to polar form, we should pay particular attention to the angle to make sure that both of these are in alignment. Excuse me. So this is conversion between polar form and rectangular form of a complex number. Okay, so that is what we discussed in the last class. We're going to look at some examples of that. In addition to this, what else did we do? We also did this, right? The VRMS, if I have a cosine wave, sinusoid, V equals to Vm cos omega t plus phi, okay? The frequency of this guy, is omega, okay? Omega is the frequency, Vm is the amplitude, and VRMS, root mean squared of this guy, is simply Vm over square root of 2, okay? This is an average, an integral of the squares of the function, and then the square root. Okay, so we found the VRMS value for this guy. Then we also did RLC in frequency domain. Okay, as we found out, for R, L, and C, for all the three circuit elements, the VI relationship is going to appear like V is I times Z. Okay, it appears pretty similar to the Ohm's law relationship. Okay, we'll find out how to calculate the impedance of each of these. Okay, so when it comes to resistance, okay, let's say I'm applying a current equals to Im cos omega t. My bad, sorry, plus theta I. Okay, let's say that is the current I'm applying. Okay, what I want to find out is the voltage across this guy. We know voltage is I times R. So when you do the mathematical solutions, what you'll see is I or V. Okay, this guy is time varying signals are shown using lowercase. Okay, V is R times Im cos omega t plus theta I. Okay, so what we can do is V is IR equation holds good for resistance. Okay, this is for resistance. So let's see resistance in frequency domain. Okay, what you will see is that the current and the voltage are in phase. Okay, there is no phase shift between the two. That's the idea of resistance in frequency domain. Let's see inductor. In frequency domain. Okay, when you do the inductor in frequency domain, let's say I'm applying a current of I equals to Im cosine omega t plus phi. Okay, we know in order to find out V, we have to do L di by dt. Okay, if we go through the math, we are going to end up with an expression that looks like V equals to j omega L times Im cos omega t plus phi. Okay, if I call all of this as theta I, so meaning that, okay, meaning that the voltage is I times, so this is all I, right? So voltage is I times this complex number j omega L. Okay, so we like to call this guy as the ZL. So if I call this as ZL, then I can write this expression as V equals to I times ZL. Okay, where ZL is given as j omega L. Okay, so that's the idea. Okay, voltage leads the current by 90 degrees. Okay, meaning that if you were to express this in a polar form, the phasor equivalent of this, if you do the capital boldface V to represent the phasor, okay, if you were to do the phasor equivalent of this, what you will get is V is omega L Im times Im angle theta I plus 90 degrees. Okay, so these are two representations. So one is the rectangular form, like a complex number that has some imaginary component to it, j component. Similarly, there is also a polar form. Okay, it's also a polar form that is. So this is of interest to me, and omega L is of interest to me. So this is the polar representation, which shows you that the inductor leads the current by 90 degrees. Okay, there is a phase of an added phase of 90 degrees over there. So this is the inductance in frequency domain. All you have to remember is this equation. It's very similar to the Ohm's law. V is I times ZL. Okay, ZL is called the impedance of an inductor. Okay, omega L is inductor reactance. Okay, so we look at some problems for this later on. Okay, let's look at, this is something we did in the last class. Let's look at capacitor in frequency domain. Okay, let's have a capacitor in frequency domain. Okay, what we got is we are given a voltage V equals to Vm cos omega t plus theta V. Okay, we are given this guy. When I'm applying the input of a voltage, I'm interested in finding out how the current appears. Okay, so if you do the calculations, you'll find out that I or V, okay, the phasor equivalent of V is going to be 1 over j omega c, 1 over j omega c times I. Okay, so the relationship between the voltage and the current in a capacitance is pretty similar to what we have seen here. V is I times JL, right? I times ZL. So if I am to write this guy, okay, all of this guy as ZC, I would see V equals to ZC times I. Okay, so all of this should be pretty similar to the Ohm's law. Okay, the current voltage relationship should be defined through the resistance value. Similarly, the complex resistance of a capacitance can be given as 1 over j omega c. Okay, that's the idea of capacitor in frequency domain. So this is a rectangular form. If you were to express it in a phasor form, you'll see that the capital V, okay, the phasor V, okay, is Im over omega c angle theta I minus 90 degrees. Okay, so what you have to remember is current leads the capacitance, leads the voltage in a capacitor by 90 degrees. See, the voltage, there's a negative 90 degrees phase over here. Okay, so in effect, I have Eli the Iceman. Okay, this negative 90 degrees is coming from the fact that J is in the denominator. If you were to translate that to numerator, you have negative J over omega c because J squared is 1, negative 1. Okay, using that relationship, we can translate all of this into phasor form. Okay, even if an, not 100% of this makes sense, I ask that you bear with me. Okay, I ask that you bear with me because it's going to become more and more clear when we do some problems. But this is how far came in the last class. We did one example maybe of converting a circuit into its equivalent frequency domain representation. Okay, so let's do some problems here. Let's do some example problems to really consolidate these concepts. Okay. Okay, let's do some example problems. Let's start small with an inductor. Okay, an inductor is given, and the current flowing in an inductor is given to be, okay, the current flowing in this inductor is given to be 10 cosine 10,000 t plus 30 degrees milliamperes. Okay, the inductance value is given to be 20 millihenry. Okay, so these are given. Okay, now you're asked to find out the inductance reactance. Okay, now I'll show you by example what these are. Okay, then you're also asked to find out the impedance. Impedance is nothing but the complex I resistance. Impedance of inductor. Okay, what's that value? the phasor voltage across the inductor. What's that value? Okay, and then an expression, the time domain expression. Okay, so let's go back to, so these are the four terms that we are asked to find out. So inductance reactance. Inductance reactance is nothing but this term over here. So we are looking at only the okay, the terms that correspond to inductance. Let's see. Okay, I'm only looking at that part. Okay, now there's a term here, J omega L, which I defined as ZL. Okay, ZL is impedance of the inductor. Okay, and omega L is simply called the inductance reactance. Okay, so this guy, inductance reactance, is nothing but omega times L, and the impedance of the inductance, ZL, is J times omega L. Remember, if we want to find the phasor voltage across the inductance, we have to apply V equals to ZL times I. Okay, V equals to ZL times I. And once we have that, we should be able to express it in time domain. Okay, let's see. What's the value of omega?
10,000, wasn't
it? 10,000, thank you. Omega is 10,000 radians per second. Okay, so once we want to find omega L, which is the inductance reactance, it's going to be times 20 millihenry. Okay, because the value of L is given to be 20 millihenry. Let me do this. Okay, 20 millihenry. So which comes out to be, omega L comes out to be 200 ohms. Okay, so that's part A. Part B is we are supposed to find, okay, part B, J omega L, which is the ZL, okay? The inductive impedance of this guy is simply J times omega L, which is 200 ohms. J 200 ohms. Okay? Notice that inductance reactance, inductive reactance, and impedance, both of these have units of ohms or resistance. Okay, now we are expected to find, we are asked to find the phasor voltage V, the phasor voltage V. Unfortunately, we have an expression for that. Phasor voltage V is ZL times I. That's simply the phasor voltage. Let's quickly add a page here. Okay, once you do that, ZL times I, which is J times 200 ohms times I is given, right? I is given to be this guy. Okay, what I'm going to do here really quickly is convert this guy. Okay, convert this guy to a phasor. Okay, so the phasor equivalent of this guy, I, is going to be simply 10 angle 30 degrees. Okay, 10 angle 30 degrees is going to be the phasor of my Okay, now let's see how I can find out how I can use this. This is the current in the inductance, right? So I can use this, copy this in the expression down here. V is Z times IL. So that is J into 200 omega times this guy. Okay. So both of these are in two different forms. One is in the rectangular form and the other is in the polar form. Okay. So this guy, all of this guy is I, or the current through the inductance. Okay. This is the impedance ZL. Let me see if I can convert this guy ZL into angle. Okay. If I want to convert it into phasor form, this guy, okay. So the real part is going to be cos. What would be the angle here? Okay, the angle would be, there is no real part here. Remember, see, there is no real part, which is 0. So tan inverse of real part over, or imaginary part over the real part. So that's going to be 90 degrees. Infinity, tan inverse of infinity is 90 degrees. So what I'm doing is converting all of this, the phasor, into rectangular form, or the rectangular form of ZL into phasor form. I'm going to leave this guy as IL as it is, which is 10 angle 30. So this is simply the amplitude. This is the phase angle. So because that was given to us, amplitude, phase angle. So I took a phasor transform of this guy and got a phasor equivalent of it. Okay. Now once I convert this, it's going to and then the uh, magnitude of this guy. So all of this is 10 angle 30 milliamperes, right? So remember, the current that was given to us was milliamperes. Okay, current given to us was milliamperes. Now, this is the magnitude. The magnitude of this guy would be square root of 200 squared plus 0 squared whole root 200 squared plus 0 squared under root. Okay, that would be the magnitude. Okay, so which comes out to be 200. So 200 angle 90 is ZL expressed in phasor form times 10 angle 30 degrees, of course milliamperes, is the current expressed in, I sometimes call it IA, sometimes call it IL. So all of this effort is simply to calculate VL. V is ZL times IL. All I have done is to convert this guy from a rectangular form to a polar form. That's all there is to it. Okay, so once I do that, the convenience of polar form is that when I'm doing a product of two numbers in polar form, what I do is to multiply their magnitudes. So I have 200 times 10. Don't forget the milliamperes over here. And when it comes to angles, I simply add them. Okay, 120 degrees. Okay, so that's the idea. So VL is now therefore 2, okay, 2 times angle 120 degrees. Okay, so this is the phasor form of the inductor voltage, the voltage across the inductor. Okay, that is what we were asked to find out in C. Okay, in C we were asked to find the phasor form of the voltage across the inductance. Okay, we are asked to find out V, and we eventually arrived. How do you write the time domain expression for this? Okay, the time domain expression for this. So question number D is time domain expression for voltage across the inductor. Okay, voltage across the inductor is simply converting this guy back to time domain. Okay, so that means when I'm writing this V, I simply have to write the cosine equivalent of e to the j theta, okay? E to the j theta, I have e to the real part of e to the j theta gives me the cosine, right? It's the cos theta, okay? So when I'm doing that, I simply have to, when I'm expressing this guy, okay? When I'm expressing the VL in the time domain, all I have to do is to take the magnitude cos omega t plus this angle 120 degrees. Okay, so this is the expression, time domain expression for voltage across the inductor. Okay, but we know omega t, omega to be 10,000, right? So this is the answer to part D. Okay, this is part D. Okay, this guy is part C. Okay, this is C. Okay, so on and so forth. Okay, this is part B. Okay, this is part B, and then this is of course part A. Omega times L, which is 200 ohms. Okay, so let's do another problem. We'll do another problem here. Find the phasor transform of, let's do one more problem that's not directly related to inductance, but it's still doing the phasor transforms. Okay, let's see if I can, I'll do one more problem, one simple problem, and then move on to another problem, example 2, another, a bit more complicated problem. Okay, example 2, find the phasor transform of so we are asked to find the phasor transform of a bunch of different voltages and currents. So the first one is V is 170 cos 370 minus 40 degrees. Okay, so if you want to find the phasor transform of this guy, that's straightforward. All you have to do is to look at 170, which is the magnitude, and the phase angle negative 40 degrees. So that's the answer. Okay, let's see if I can use a different. Okay, so that's the answer. The first part is easy part. Let's see if we can do another one. Okay, this guy. I is 10 sine 10,000 t plus 20 degrees. Okay, and we're asked to express, this is time domain, right? Because I see this variable t over here, okay? This time domain, and I'm expected to convert this to frequency domain into phasor form. We have to take the phasor uh, transform of this guy, okay? So in order for me to be able to do this, I have to begin by noticing that this is a sinusoid, sine wave. I want to convert it to a cos, okay? So in order to convert it to a cos, still in time domain, I'm going to write it as cos 10,000 t plus 20 degrees minus 90 degrees, okay? The reason is sine theta is cos theta minus 90. Okay, using that identity, I express this guy. Now it's a matter of observation. It's just noticing that, let's see. Once I have this, I should be able to write the phasor equivalent of that as 10 and minus 70 degrees. Okay, so I simply grab this value for here and then this value for here. Okay, that's the phasor. That's exactly the same as here as well. Okay, let's see. Let's say phasor transform. Let's see if we can do one more. This guy. Okay, C. Okay, one more problem of converting this guy 5 times cos omega t plus 36.87 degrees plus 10 cos omega t minus 53.13 degrees amperes. Okay, I is given to be this guy. We are expected to find the, so this is the time domain equivalent. Okay, we are asked to find the phasor. Okay, how would we go about doing that? So here is a general procedure I have. When I have sum of two sinusoids, it's not all that straightforward. I cannot simply add the angles here, or I cannot simply add the magnitude here. So the sinusoidal arithmetic is a bit more complicated. So what we do is to conveniently transform it into the complex number domain, okay, frequency domain, where the arithmetic is much more easier. Okay, let me copy this over. I'm going to copy this over here. Okay, and then so my approach is to convert this guy to a complex number or phasor. Let me translate this to a phasor first. So it will be 5 angle 36.87 degrees plus 10 angle negative 53.13 degrees. Okay, remember when I had a product of two phasors, okay, you can take this as a generic procedure. When you see the product in two phasor terms, well, that's very easy to do. Okay, I can simply multiply the magnitudes and I can simply add the angles. Okay, so that would be 36.87 minus 53.13. So the product is very straightforward in phasor form. Okay, not so much in the addition form. Okay, adding phasors is not straightforward. So when we have phasor arithmetic, that is addition arithmetic, we want to convert this guy to rectangular form. So addition is easy, rectangular form. That's the observation. That's the premise that underlies all of our conversions. When we are converting crazy, like time domain to phasor domain to rectangular form. Okay, that's based on the observation that addition is easy in rectangular form. Product or multiplication is easy in phasor form. Okay, so we have an addition operation here. So I better convert this guy into a rectangular form. So in order to convert this guy to a rectangular form, I have 5 cos 36.8 plus j 5 sine 36.87 degrees. Okay, corresponding to this guy plus, okay, corresponding to this guy, I can write 10 cosine negative 53.13 degrees plus j 10 sine negative 53.13 degrees. Okay, so that's the term that represents this guy. So this is the rectangular form of the time domain expressions given at the top. Okay, the time domain given at the top. They're converted to phasor. They're related or polar form. okay? And from polar form, we converted them to rectangular form. All of that because we want to do addition operation here, okay? Now, if you look at this guy, okay, 5 cos 36.8 degrees, that guy, okay, it's easy to find a number for that. So it's going to come out to 4 plus J3. That's going to be the equivalent of this guy, okay, plus, now this is 6 minus J8, okay. When you plug these numbers into your calculator, you'll see that all the green area, that rectangular form, complex number, simplifies to this guy. Okay, so the equivalent is that I can simply add the real parts, 10, and add the imaginary parts, j, negative 5. Okay, so this is the rectangular form. This is the rectangular form of the sinusoid of the input that has been given to us. So all I have done is to simply translate the sinusoid into phasor, phasor into rectangular, and then add them up in the rectangular domain, the rectangular form. Now we can convert this back to phasor. Okay, we can convert this to phasor form, which comes out to be in order to do the phasor transform, what you have to do is to square root of 10 squared plus 5 squared will give you the magnitude, okay? Tan inverse of imaginary part over the real part will give you the phase, okay? Will give you the phase. So when you write it out, it's going to come out to be, so it's 10 squared plus 5 squared under root is going to come out to be 11.18. So when you want to write it in phasor form, A angle phi, that can be expressed as 11.18 angle tan inverse of half. Okay, that's going to be negative 26.56. Negative 26.56 is the phasor representation. That's what you wanted to do, right? Find the phasor transform. The problem asks you to find the phasor transform of an addition of two cosines. When you have an addition of two cosines, you want to translate them to phasor form. The addition is not straightforward in phasor, so you conveniently convert them to rectangular form, where you can add the real and imaginary parts. And then when you convert it back to the phasor domain, so that will be your answer. Okay. How do you do the A, the magnitude? Magnitude is simply the square of real part and the imaginary part. Okay, that's the magnitude. How do you find the angle? Phase angle, that's the tan inverse of imaginary part over the real part. Okay, questions, please. Okay, let's see if we can do one more problem, converting from time domain, from phasor form back to time domain. Okay, so far, this example has been conversion from time domain to phasor form. We'll do another problem here, which is converting from phasor form to time domain. Okay, the example that we are going to look at now is the other way around. The third problem is to convert from phasor to time domain. Let's start with a simple form. Find the time domain expression. Okay, an expression that looks like this: x equals to a times cos omega t plus phi is what we want to find out for each of these phasor forms here. B is 18.6, angle negative 54. Okay, well, that's straightforward. Writing the phasor equivalent, the time domain equivalent of this is simply 18.6 cosine omega t minus 54 degrees. Okay, so this angle is the phase angle, and this guy is the magnitude. Okay, let's do another one. Let's do another problem. That's a bit more interesting. Something like this. I'll give you the phasor form and I ask you to find the time domain expression for that, which is 20 angle 45 degrees minus 50 angle negative 30 degrees milliamperes. So we are expected to write the time domain equivalent of this. Well, let's first notice that there is an arithmetic, a subtraction between two phasors. Okay, so we cannot directly subtract phasors, so we have to convert them to rectangular form. Okay, there are two phasors here. There is one is that guy, the other is this guy. So I'm going to come up with two rectangular form expressions. Okay, so 20 cos 45 degrees plus 20 j sine 45 degrees is the rectangular representation of the one on the top minus 50 cosine 30 degrees, negative 30 degrees, but cosine of negative 30 is the same as cosine of positive 30. Okay, let me write it this way. Cosine of negative 30 degrees plus j times 50 sine negative 30 degrees. So I converted this guy. Okay, I converted this guy into rectangular form. Okay, all I have done is there is the angle, there's the magnitude, there's the angle. Okay. Okay. Now, once I do that, I should be able to do the math here. So this is cos 45. I can plug that number into the calculator, which is 1 over square root of 2. So when you do the arithmetic, you'll end up with something that looks like negative 29.16 plus j 39.12. Okay, when you simply add the real part and the imaginary part, the sum, the arithmetic operation, the subtraction of the two components here gives you this part. Okay, when you plug that into calculator, okay, let's be very careful here. So this is negative 29.16 plus j 39.12. And when you convert that into a polar form, you get 48.81. That is because when you want to convert this to a e to the j theta or angle theta, a angle theta or phi, a is given by the square root of 29.16 squared plus 39.12 squared. Okay, that's the magnitude. So which comes out to be 48.81. Now you want to find angle theta. Theta can be found out by tan inverse the imaginary part, 39.12, over the real part, negative 29 point, okay, negative 29.16. Okay, when you do that, it's going to come out to be negative 53.32 degrees. So when you plug in tan inverse of negative 39.12 over 29.16, okay, your calculator is going to tell you that 53.32 is the angle that corresponds to that value. But there's a problem here. The angle is negative. Okay, the angle is negative, implying that the imaginary part should come out to be negative. Okay, because if you convert it back to the polar form, it should come out to be 48.81 cosine negative 53.32 plus j 39.12. It should come out to be 48.81 into sine of negative 53.32. Okay, as it turns out, the angle here is not consistent. I have a problem with the negative sign of the angle. Okay, when I plug it back and convert it back to the rectangular form, I see that the cosine of a negative number turns out to be a positive number. So I'll get a number that looks like 29.16, okay, minus j 39.12. Okay, so these two are not consistent. I convert it to phasor form and convert it back to polar rectangular form, then I'm not getting the same result. That's owing to the fact that I have a negative. Now this guy is in the second quadrant, so what I want to do is to add 180 degrees to this guy, just so the results are consistent. Okay, once I do that, the results are all going to be consistent. Now the resultant phasor is 48.81 and the angle is 126.68. Now I can convert it to time domain, 48.81 cosine omega t plus 126.68 degrees is the time domain equivalent. That is what we wanted to find, right? We wanted to find the time domain, phasor to time domain. So we
Professor,
started with the phasor. Yes.
real quick, why did we add the 180 degrees?
Yes. Yes, that's a good question. I was hoping somebody would ask.
I just want to
Okay.
verify, are we like just straight flipping direction, so to speak?
Let's see. In the four quadrants, quadrant 1, quadrant 2, quadrant 3, and quadrant 4, all the trigonometric functions are positive here, right? So if I have sine 30 or cosine 85, they're all positive, right?
Yes.
So when you go into the second quadrant, sine is positive, cosine is negative. Okay, cosine is negative. Now the tan is a positive here, so both sine is negative and cosine is negative. Okay, in the third quadrant, so tan is positive. Okay, in here, the cosine is positive. Okay, the cosine is positive, sine is negative. Okay, so what happens is, if you look at the rectangular waveform here, okay, if you look at the rectangular expression that you have, okay, you see that the real part is negative, okay, and the imaginary part is positive, right?
Okay.
So real part corresponds to the cosine and the imaginary parts corresponds to the sine, right? So in what quadrant is the cosine negative and sine positive?
Quadrant 2.
That's in the quadrant 2. So I have to add 180 degrees just so the angle here is translated into the quadrant 2
Oh,
from the
okay.
third quadrant.
I see what
Just so
happened
we
there.
are existing in the second quadrant.
Okay, thank you.
Yes. Okay. Now, so the idea is the reason for adding 180 degrees is to make sure that our answer is consistent with the signs here, the polarity of plus and negative over here. We'll do one more example with that, and then things will become clear. Okay, let's do one more example. I'll add a page here, and then we'll convert, which is still problem number 3. We are expected, or problem number 2 is it? Problem number 2, example 2, conversion from time to phasor. No, not that guy. Problem 3, conversion from phasor to time domain. We looked at 2 examples. We look at C as well. We look at another problem here. V is 20 plus J80 minus 30 angle 15 degrees volts. And we want to write it in time domain. We want to write it in the time domain. Okay. When we want to write it in the time domain, I don't have to convert this guy because notice that it's a subtraction here. Okay. This arithmetic is better done in the rectangular form. Well, this is already in rectangular form, so I don't have to touch it. I only have to change this guy. Okay, so it will become 20 plus J80 minus 30 cosine 15 degrees plus J30 sine 15 degrees. Okay, so that's the conversion from the polar form to rectangular form. Okay, that's this guy. Okay, once I do that, I have 20 plus J80 as it is here. Now 30 plus J50, you can do the math and it comes out to be, and you can add the real part to the real part here, and you can add the imaginary part to the imaginary part over here. Okay, so on and so forth. When you do that, you get something that looks like 9 plus J 72.2. Okay, 9 plus J 72.2. Now, and you express that, what happens is when you convert it to, so this is in the rectangular form, when you convert it back to the phasor form, what you will get is 9 squared plus 72.2 squared. Under root of that will give you the magnitude. The angle is going to be given by tan inverse of 72.2 over -9. Okay, so that's going to be the imaginary part over the real part will give you the angle. Okay, so when you do that, it's going to come out to be 72.76 angle -82.9 degrees. Okay, -82.9 degrees. So let's see if this is in fact the true or not. It turns out that when I plug in, see, notice that this guy, this negative sign does not represent a negative of the real part. Okay, so if you think about it, 72.76, if you try to convert it to rectangular form back, it will give you cosine -82.9. But cosine of a negative number is still a positive number. So you're going to end up with a positive real part, which does not match up to what we started off with. Okay, so in order to do that, what you simply have to do is to add 180 degrees to bring it into the second quadrant. Okay, so how can I simply just add 180 degrees and the values are going to be the same, okay? Cos the number, add a number x, you can add with add 180 degrees to that, and then it's just the inverse of that guy, okay? So all you're doing is flipping the magnitude, not the magnitude, but the polarity over here. Okay, so when you do that, the phasor form is going to be 72.76, angle 97.11. But that's not what you want. What you wanted is the time domain expression. Okay, now it's easy to write the time domain expression for this 72.76 cosine omega t plus, that's the answer that we are looking for D. Okay, so all I have done is to simply convert the polar form to a rectangular form, do the arithmetic, convert it back to a polar form, so I can make one quick jump to the time domain expression. Okay, does that make sense?
Yes, thank you.
Okay, let's do one problem. Let's do one problem here. Let me see if I can. Okay, we'll do a capacitance problem. So we'll do a capacitance problem here. Let's see capacitance in frequency domain example. Okay, have a capacitance. The value of that capacitance is given to be 5. The capacitance of that capacitor is 5 microfarads. Okay, the voltage is given to be 30. Okay, I better write this as a little bit 30 cosine 4000 t plus 25 degrees volts. Okay, so what we are asked to find out is the capacitive reactance. What is the reactance of this guy? Okay, and then we're also asked to find out the impedance of this guy. Impedance of the capacitor. Okay, and then we're asked to find out I that's flowing through the capacitance in phasor form, and then the time domain expression for I. Okay, the time domain expression. Okay. Okay, let's see if we can begin. We'll go back. Okay, let's go back to the capacitor. We go back to the capacitance a few pages back. Okay, so look at this equation. Look at this term. Okay, now V is 1 over j omega c. Okay, that guy. Okay. 1 over omega c is called as the um, capacitive reactance. 1 over j omega c is called the impedance of the capacitance. Okay, so we'll use that notion here. Capacitive reactance is 1 over omega c is the capacitive reactance. The impedance of the capacitance is 1 over j omega c. Okay, that's it. That's all there is to plugging in the numbers. So let's see if we can find in this case, the omega is given to be 4,000. Okay, omega is given to be, is it 4,000 or 40,000? Let's take it as 40,000, an additional zero. Okay, 40,000. So in order to find a capacitive reactance, all we have to do is 1 over omega times C. This is 1 over 40K times C is given to be 5 micro. Okay, which comes out to be 50 ohms. Okay, this comes out to be 50 ohms. Okay, now if you do 1 over j omega c, so 1 over j omega c, so that's going to be 1 over j times 1 over omega c. 1 over j is negative j, and 1 over omega c is 50 ohms from the previous step. It's all there is to it. Okay, now can we do the ci? Okay, I. How do you find the I? We know V equals to ZC into I. This guy is ZC, right? B, ZC. Okay, ZC into I. Okay, so in order to find I, all I have to do is V over ZC. Okay, that's what we have to do. Add a page here. We have to do V over ZC. So I, the phasor of the current flowing in the capacitance, is V, the voltage across the capacitance, times the impedance of the capacitance. Simply like I equals to V by R in a resistance. Okay. In frequency domain, a lot of things become simple. A lot of things become complicated. So if you know what things are easy, you don't have to go through that. You don't have to go through the differential equation. C dV by dt. You don't have to do that. I equals to C dV by dt, right? You don't have to go through the derivative. This is what you would do in the time domain. But in the frequency domain, what you can simply do is I is V over ZC, where ZC value, you already calculated to be 1 over this guy, negative J50. Okay, negative J50. Let me see if I can do the arithmetic. What's the V given to be? V is given to be 30 cosine 40,000 plus 25. So 30 cosine 40,000 plus, is it 25? 25 degrees in the time domain over ZC, which is negative J 50 degrees, 50 ohms. Okay, let me see if I can convert this time into phasor. Okay, so V over ZC is 30 angle 25 degrees, right? Simply 30 for 30 and 25 for 25. Now what I'm going to do is the observation that there is a division here. There is a division here. Division is easier done in polar form. So I'm going to convert this guy, I'm going to convert this rectangular term into a polar form. Okay. So in order to convert this negative J50 into a polar form, the magnitude is going to be 0 squared plus 50 squared under root. So the magnitude is going to be 50. Okay. And then the angle tan inverse of the real part is 0. The imaginary part is some number. So tan inverse of infinity is really 90 degrees. Okay. So I can plug these two in the equation above and say This is simply 50, angle 90 degrees negative. Does that make sense? So all I have done is to, earlier in the problems, when we had the addition operation between two complex numbers or two phasors, we converted them to rectangular form or complex number form because the addition operation is easier in that domain. But in here, a division operation is much more easier done in phasor form. Okay, so what we get, V over ZC, what we get is V over ZC is, what we can simply do is this guy. Division in phasor form is simply division of magnitudes and addition of angles. Okay, addition of angles. Because this is in the denominator, I have to subtract. Okay, so that's one negative, and there's already one negative coming from that guy. Okay, this guy. So denominator. That's the idea of division in phasor form. Okay, you simply, division means you simply subtract the angles. So V over ZC, which is I, and that is what I'm after. Okay, that's the problem. That's what the problem asks me to find. 0.6 angle 115 degrees. Okay, so this is the phasor form of the current. Let's see if this is what we wanted to find or not. Problem says, what's the phasor? I. Now, the problem next part is the time domain part of it. Well, time domain part of it is easy. The time domain part is simply 0.6. That's coming from here. Okay, that 0.6 shows up here. Cosine omega t plus 115 degrees. Now you know omega t to be, that was given to be 40,000, right? So 40,000 t plus 115. This 115 is coming from the fact that the phase angle has been evaluated to be 115. Does that make sense? So this capacitance here, when you convert it to frequency domain, okay, when you convert it to frequency domain, you can simply use V equals to IR or V equals to IZC formula, where ZC is simply 1 over j omega c. So inductive capacitance is ZC, okay, it's defined as 1 over j omega c. Okay, so inductive capacitance is so resistance in frequency domain acts as a resistance. Inductor acts as an impedance ZL given as j omega times L. Capacitance acts as an impedance given by 1 over j omega c. Okay, so circuit elements in frequency domain. Okay, that's all there is to it. And using that, we found out 1 over j omega c. Omega c is the capacitive reactance. Okay, questions, please. Okay, I welcome you to look at some more problems. Okay, what we can do is to move on to talking about Kirchhoff's laws in frequency domain. All of these apply. We can look at some examples. We look at some series parallel simplifications, which is straightforward. Okay, and we looked at all of these. All right, rectangular form to polar form. How do you convert from one to the other? You get the magnitude by doing this, that guy. You get the phase by doing tan inverse, tangent inverse. Okay, how do you convert from rectangular form to polar form, back and forth? You know that. Okay, we looked at some examples here. So I welcome you to look at some more examples that are present here and an explanation of why we want to add that 180 degrees, okay? Just so we are located in the right quadrant, okay? Then we'll come back in the next class to look at the Thevenin's equivalent and Norton's equivalent circuit analysis in frequency domain, okay? Questions, please. We'll come back and do that on Monday. What questions do you have at this time?